Hello everyone, today we are going to analyze depth first search algorithm. After that, we use it to find a path in a graph between two nodes, start and goal nodes. Later on, we are going to write a Python code to give us this path. First of all, what is depth first search? Depth first search is an algorithm for traversing or searching a tree structure or graph. It is uninformed search, like breadth first search, that progress by expanding the first child node of the search tree that appears and thus going deeper and deeper until a goal node is found or until it hits a node that has no child. So what happens when it hits a node that doesn't have child? It is going to start going back. The search backtracks, returning the most recent node it hasn't finished exploring. So its strategy is simply to go forward in depth while there is any such possibility. If not, then backtrack, means move back and choose another path. So before starting depth first search, we need to remember to stack two data structure concepts. These are data structures. They are stack and queue. Stack and queue are both the non-primitive data structures. The main difference between stack and queue are that stack uses last in first out method to access and add data elements, whereas queue uses first in first out method to access and add data elements. So stack has only one end open, this part, for pushing and popping the data elements, but queue on the other hand has both ends open for enqueuing and dequeuing the data elements. For depth first search, we are going to see we will use stack methods. To clearly see how depth first search explore the search space, we will use search and tree graph at the same time. So you can see how the branches is opening one by one. So strategy will be expand the deepest node first. The implementation will be fringe is going to open is a last in first out stack. So our stack is here, and at the same time we can see how the stack is going to be fill up and empty. This is our start node, this is our goal node. So our aim by using depth first search, find the path. In the graph you can see that they are all one way directed. Branches we have, edges we have, and there is another restriction here. The ties will be broken in alphabetical order. So this S node has three children, D, E, and P. So alphabetically D comes first, then we will explore D first. It is only for this case. It doesn't need to be one-directed search. Perhaps you might have two-directed search graph, two-way edges. So it means you can go from S to D and D to S. But in this case, you can only go from S to D and you cannot come back from D to S. Now let's start exploring our graph by using depth first search. We start from S. After S, we are going to have three children here, and alphabetically D comes first. So first we are going to explore D. You can see we put all the possibilities here, and before putting all the nodes, all the paths in stack, we are removing the S. We are popping up. When we pop up, it is not going to be in the stack anymore. After that, we insert all the nodes, and first we started from the last child, then previous one, and the first one. Why? Because when I pop, I'm going to pop the first one. The last come will be served first. So D is at the top of the stack. When I pop, it is going to get the D and explore all the children, add them all in our stack. In this case, B will come first, so B will be at the top of the stack. C will be just after that one, and E will be the last among these children. Now we are going to pop again B and write its children. It has only A. It is at the top again. There is nowhere to go after A, then we remove this path from our stack. Now, which one is in next? Which is going to be next? The STC is the next one. We open STC. After C, there is only one key children, it is A. Child will be added here, and this is our path now. We check the A. Is there anywhere to go? No. Then we remove that path again. So this path is not going to be in our stack. Which one is next now? SDE. SDE. We can see from here to SDCA. We stuck here. Now we didn't explore this children. We are going to explore that one. After SDE, there are two kits again. We just add them on the stack. The first one will be R, the second one will be H. So H will be at the top of the stack again. Then when we pop, we are gonna get that one. So we repeat same process again and again until we reach G, which is our goal. Okay. Then we have seen there is nowhere to go. We remove that one from the stack. Now we have G here. We edit there and we check to ask the question, is G our goal? Yes. Then we stop here. As you see, we didn't use stack at all. For such a problem, if we use breadth first search, it wasn't going to be enough that much size. We were gonna need the longer one. But in depth first search, it is very space friendly algorithm. It doesn't use any space at all. So this is depth first search. Where do we use depth first search? We are using depth first search like chess-like games, chess-like applications. Imagine this is your queen. You have 3 movements and you pick one of them, then another one, then another one. Then you have seen that you failed. Then you can backtrack. So you had another 2 options here. Then you try them all one by one. Whenever you reach goal, then you say, okay, you won, and you can stop. So this is very nice algorithm that we are using in chess, like games or applications, let's say. Now step by step depth first search algorithm. Again, to clearly discuss the algorithm, the first previous graph is a little bit bigger, so it will be difficult to put them all here. I prefer this small one. That's this graph. There are 6 vertices, nodes, and 8 incidents, one-way directed edges with no assigned edge weights here. So the first problem, how are you going to represent a graph in Python? There are 2 popular options for representing a graph. The first being an adjacency matrix, effective with dense graph. When you have bigger than this one, when you have very dense graph, it is better to go with adjacency matrix. But for such small graph, we can go adjacency lists. It is very effective for sparse graphs like that. I have opted to implement an adjacency list which stores each node in a dictionary along with a list containing their adjacent nodes like this. So each node will be key, and each key will have a list value. That list is going to contain the children of that parent. C, as you see, C doesn't have any child, so we didn't put anything here, and G doesn't have any child, so we didn't put here anything. And by the way, break the ties in alphabetical orders. That's why we put A first, B second. But in depth first search, we are supposed to put B first, A second. We will come to that one later on. So now we are ready to find the shortest path with DFS, but before that one, let's have a look at the pseudocode of our algorithm. First, we are going to initialize stack with search node S and only entry. There will be only one node there. And visited will be again S. Whatever in the stack, it is going to be directly in the visited. There will be a while loop here. It is going to check the stack. If it is empty, it means you failed. Else, pick some search node from N, node N from stack. If state N is a goal, G, then return N. We reach the goal, so we can break the loop and just return the path. This is our path. Otherwise, remove N from stack. Find all descendants of state N not in visited, and create all one-step extensions of N to each descendant. Add the extended paths to stack. add children of state N to visit it, then go to step 2 again. Let's have a look here, step by step. This is our graph, dictionary representation of our graph in dictionary, and stack and visit it here. We just put S in our stack as a list. Whenever something in a node in our list is in a stack, it is going to be visited automatically. Now we explore. After S, there are two children, A and B. We are going to get SA one list, SB another list, and add to stack. We remove S, pop the S. Instead of this list, we are going to add two lists. Both of them are children of S, but we are writing all the path, not only the children here. Then it will be very easy for us to return all paths. S to A, S to B, we put both of them here, and A and B will be in our visited list. We will carry on like that. After we pop the first list, we are going to remove it from our stack, and we are going to add the children of A, which are C and D here. SAC, SAD. Be careful, C at the top of the stack. Why? Because we are said that the ties will be broken alphabetically. We are gonna pop this one again. We will check, is there anything after C? No, there is no child at all. Then we are going to remove this one, this path from our stack. So which one is next? SAD. After there are two options, C and G. C is already in our visited list, so we are not going to write SADC. We are just going to add there SADG, one child. SADG. Now we will pop up this one again. And we check, is G is the goal? Yes. Then we don't need to explore the rest of them because our goal was to find G as soon as possible. We found it, then we can break the loop and return the path. So this is the solution depth first search return to us under these circumstances. With one made edges, ties are broken alphabetically. This is what you are going to get. I try to explain here step by step first iteration of depth first search algorithm. In first iteration, stack will get just as here. Visited will be empty. Path stack pop 0 is going to pop the first list, and this list will be assigned to path. Now we need to get the node in that list, that node where we are now. This is the last element of that list. In this case, it is going to be S, but this is string. That one is list. Be careful. Is this not the goal? If it is yes, stop and return. It is no, then gets its children and add to queue. So since it is no, we are going to get its children. How we are going to get? We are going to call by using this node as a key, we are going to call the values of that key. These values will be children of that node, which are B and A. As you see, I put them in the dictionary in reverse order. So I will get SB first, then over SB I am going to stack SA. When I pop, I am going to pop SA first. This is important in this problem because we say that the ties are broken in alphabetical order, so I am supposed to explore A before B. Each child should be added to the path separately. So we are gonna do this one for SA and SB. This is a nice way to do it easier. We will call this one in Python. I will explain there. Path plus child, I put here in a list because child is just a node here. This is just a string. You cannot do operation between list, such an operation between list and string. You have to cast to this one to list. Then stack the children in the stack. So this is after first iteration, how your stack will look like. We will add A and B to visited list. After that, go back to second step and repeat them all until you find the goal state. Whenever you find goal state, you are going to break the loop and return the path. Now it is time to write in Python